Good afternoon, Science 30. So this is going to be the second lecture in the Ecology series. I'm going to talk about population growth. So today I'm actually going to talk about a bunch of equations and graphs. And then we'll finish up the last part of ecology in another lecture looking at ecological relationships. So this is for sure going to help you with poaching. So I'll be connecting that theme for your project to the lecture a bit today as well. I'm going to do a couple examples and then tie this into your project as well. So this starts on slide 45, and I might get from slide 45 to 65, but if anything, I won't get that far. I won't get to our case-selected. Our case-selected species. So think slide 45 to 65, and I'll finish the rest off of this unit in a separate lecture. So what I want to direct you towards in your key is data booklet, first and foremost. So these equations, which if this were normal times, I need to grab a pencil. Okay, sorry, if these were normal times, you'd need to know all of these equations. So population density, Hardy-Weinberg, population growth, growth rates, CGR is per capita growth rate. So these are all in the back of your key. Okay, so the first equation that I'm going to discuss is population density. This is a very, very simple equation, and it's already something that you've seen throughout your time in formal education, basically. So I'm just going to do a quick density question for you. So if you look on page 141 of your textbook, the population density question basically is just looking at how many organisms exist within a certain area. And that the area could be meters squared, kilometers squared, cubic centimeters. It could be a volume, right? So that's what we're looking at here. So this question says Lac La Biche is one of the largest lakes in Alberta, covering an area of 234 square kilometers. Over the past century, intensive commercial and sport fishing practices have threatened the walleye population. Fish surveys conducted in the lake in 2003 estimated the adult walleye population at 2,800 individuals, and the desired population is 50,000 adults. Okay, so the question asks, what is the population density needed for a healthy population of walleye? So needed, right, obviously is the 50,000 adults. And what's actually present what's actually present is the actual population. So we know that there's 50,000, we need 50,000 adults in a 234 square kilometer area. So to solve this question, right, all we're doing is looking at 50,000, excuse me, right, 50,000 walleye per 234 square kilometers. Do the math. And you're going to have about 214 walleye, right, or 213.7. Right, it says record your answer to one decimal place, so 213.7 walleye per square kilometer. Okay, so that's a density question. So you're looking at the population density in number of individuals per area or number of individuals per volume. Pretty simple. I'm not going to spend much time on that. All right. Okay, so when you look at density and distribution, there's three main ways that organisms are distributed throughout Earth. And in reality, most organisms have a combination of these three types of distribution patterns. The first one is random. So you can see this. This is during the wet season on the Serengeti Plains. You may see this in the tundra with large migratory animals during summer and things like that. So here's the deal with random distribution. There's no rhyme or reason to where members of a population exist. Resources are very abundant, so it doesn't really matter where the organisms are. They can kind of go where they want willy-nilly. So this is a very temporary way that organisms exist. Clumped is the more likely way that you will see population distribution patterns, right? So members of a group are found in close proximity, congregate where food, water, and shelter is most abundant. You can see that the human population patterns, most individuals on Earth live within 300 kilometers of a coastline, an ocean coastline. About 80% of the human population does that, so you can see where the density is the greatest. You could see where density is in the world, like, where, viral transmission is a really big deal and things like that with what we're dealing with right now. So think about population distribution patterns in relation to what we would be looking at poaching-wise, right? We're going to be looking for areas with resources in order to be able to find these animals. Uniform distribution happens, again, temporarily with territorial animals. Happens when we artificially plant crops as well. So most populations don't fit any one scheme. Excuse me, you can see here, these are emperor penguins in Antarctica, male emperor penguins in a rookery. They are incubating an egg through the duration of the winter. So territorial animals will have a uniform distribution for a temporary period of time. So in reality, right, most populations have a combination of these different strategies when we look at population density and population distribution. One thing that I want to just direct your attention to as well is page 141 again, question number 10. We're looking at open and closed populations. So a closed population is where there's no gene flow, right? So which of the following statements about a closed population is true, right? So your answer would be B. So natality and mortality occur. So natality is a term that you need to know. Natality is birth. Mortality is death. Okay, there's no gene flow in and out of a population, so there's no immigration and there's no emigration. Emigration is leaving a population. Immigration is moving in. Okay. All right, so another way that you'll see population density is, I'm just going to go to the unit test that you have. So this is numerical response number 4. And you'll have NR5s attached to this as well. But the question says a team of scientists recommends moving grizzly bears to the North Cascades area of British Columbia in order to save the population. The grizzly population in the North Cascades was estimated to be only 23 bears in 2001. The goal of the recovery plan is to increase the number of grizzlies in a 9,810 square kilometer area to 150 by 2050. So another thing that you'll see is, so typically grizzlies in British Columbia have a range of about 1,000 square kilometers. So if you look at the density, it actually makes more sense to measure the amount of grizzlies per 1,000 square kilometers rather than per square kilometer, because it's unlikely you're going to find a single grizzly bear in 1 square kilometer area because they have really, really large ranges. So this question says in the North Cascades of British Columbia in 2001, what was the density of the grizzly bear population per 1,000 square kilometers, right? So we have, if we look at this question, okay, in 2001, right, there were 23 bears. Okay, and the area is 9,810 square kilometers. Right, so again, it's an easy question. But you'll have 23, so we find the density, right? 23 bears per 9,810 square kilometers, and then we'll get bears per square kilometer. All right, when we solve for that, you're going to get about 0.0023 bears per square kilometer. So that doesn't make any sense, right? Because you're not going to, you'll see the bear throughout its range. You're not going to see it in a very small area. So it makes more sense to solve for its range. So it's likely you'll have a bear per 1,000 square kilometer. So we're going to multiply that. So the question is bears per 1,000 square kilometer. So we're going to multiply that answer by 1,000 and we'll get the amount of bear density that we actually want. And that's about 2.3 bears, right? So you'll have approximately 2.3 bears per 1,000 square kilometers in that North Cascade range before conservation efforts began. Okay. So you'll see the density populations in relation to the actual territorial area that an animal occupies, and that just makes more sense. Okay, so that's density. Growth patterns. All right, so this is your equation for population growth. So n equals the number of individuals. Births is B, immigration is I, right? So births would also be natality. Deaths are fatalities or mortalities, okay? And then emigration is individuals leaving. So if we look at just straight increases or decreases in populations over a season, a single season, the number of individuals that either increase or decrease a population is a function of the amount of individuals being born plus the amount of individuals moving into a population. So this is B plus I, so these increase population minus the things that decrease population. So that's fatality or mortality plus individuals leaving, so emigration. Okay, so on page 140, there's a good example of this. So the question says, the black-footed ferret is considered one of the most endangered species in the American West. Captive breeding programs are trying to help reestablish a healthy population of these ferrets. Researchers have monitored the ferret populations at several sites of reintroduction. So this has the population broken up into, these are called metapopulations. So they're smaller segments of a larger population. This is pretty typical of what you'll see for this. So the question is asking, overall, what is the total increase or decrease in the population? So this is a single population, and so we have to use all of the numbers here. So it might ask something specific about did population 1, or did metapopulation 1, 2, or 3 increase or decrease? I'll show you another example that's related to that. But this one's just asking, what are the overall trends? So if I look at the question itself, I have to look at, so my overall population growth is the total amount of births, which is 9 plus 15 plus 11. So that's 35. Right, so I've got 35 births. And then there were 8 immigrants, so 35 plus 8. And I need to get rid of the amount of individuals the amount of situations where population decrease. So there were 8 plus 7, that's 15 deaths. Okay. And then emigrants is, so the amount of individuals that left is 9. Okay, so if we look at the total change or the total growth of the population, So remember, one of the big themes is change, right? So think about change. So 43 minus, this is 24, right? So we end up with 19 individuals. So the total population increased by 19. Okay, so the total population increase is 19. And that would be my answer, right? Okay. Another question related to this is here on page 129. And this is another one here that's asking, so there's different meta-populations. So you can see that. And the NR4 says, according to the information in the table, which population has experienced a decline and by how much has its population declined? So what you need to do is add up all of the different separate populations and show which one is declining and by how much, right? So if I look at population 1, okay, population 1 would have 45 individuals that increased population, and then 30 individuals that decreased population. So that one's not declining. So that's not an option. If I look at population 2, we have 55. So there are 5 immigrants and 50 births. So we look at population 2. There are 55 individuals that increase population, and then 95 individuals that decrease population. Right? There are 75 deaths and 20 immigrants. So that would be a decline of 40. So my answer is population 2 with a decline of 40 individuals. Okay. So that's your population growth equation. All right. Growth rates. You guys have seen equations like this before. So your population growth rate is a function of, so it's the amount of individuals that are increasing or decreasing over time. Right? So again, think about this when we talk about poaching. Right? It's a year-over-year decline. So overall, the trend is great, right? But a single year might not indicate that. You need to look at trends over time. So it's a function of delta N over delta T, right? And you guys have seen this when you make rate graphs, right? So this is NF minus NI over TF minus TI. Okay, so I'll give you a quick example of this. In Banff, National Park in 1895, the population of bison was 6 individuals. Right, and eventually they went extinct, right? So they were extirpated for that area. And that's why they've been reintroduced. In 2017, bison were reintroduced. And as of that year, there were 155 bison. According to the data, what is the growth rate per year of bison? Okay, so if this population were grown back from the brink of extinction to today, what would the growth rate be? All right, so when we look at the growth rate question, right, your initial time is 1855, and then right, so we have 2017 minus 1855, and that will be over what we currently have, so 155. Right, so your NF minus your initial number. Okay, and then that will give you your bison. Bison per year, right? Okay, so we will have, right, 149. And that's a 162-year span. Okay. And that's going to give me we're adding about 0.92 bison per year to the population. So that's what the growth rate would be if we had grown it from that extent, right? So some years there would have been no bison added, and some years there would have been more to get that average. Okay, so that's growth rate. So you have a set amount of time with the amount of individuals. Numerical response 5 in your unit test asking about grizzlies. It's asking about per capita growth rate. Okay, so you could find the growth rate required for this, right? So there's 23 bears in 2001. By 2050, they want 150 bears, right? So your NI would be 2001, your NF would be 2050, your time final, your TF would be 2050, and your TI would be 2001. Your initial population number is 23, and your final population number ideally is 150, right? So to find the growth rate, year over year, it'd be 150 minus 23, and that would be divided by 2050 minus 2001, and that would give you your bears per year required in order to get 150 bears. Right, so change in per capita growth rate is, right, so that's growth rate that we discussed, but per capita growth rate is actually a more important term. Okay, so it is the amount of offspring each individual contributes to the next generation. So how many offspring each individual that is of breeding age can contribute to the next generation? So how many babies each individual that can reproduce is having. Now replacement in order to replace yourself, okay, your growth rate, the per capita growth rate actually has to be a little bit more than 1. So the human per capita growth rate is about 1.7. So everyone on Earth has to have about 1.7 children. So in order to maintain current population levels, but the growth rate of the human population is greater than that. We're at like 2.4, which is why the population is still increasing. So this is a really important value when you think about animals that are being poached, right? Often it affects their reproduction because they have to travel longer ways, or they're stressed and can't reproduce and things like that. Now, lots of individuals die before they reach reproductive age, or they don't reproduce, right? So you have to have more than generally one child in order to replace the population. All right. So so per capita growth rate is a function of. See, it's shown like this, CGR. It's a function of the change in population over the initial population. So how much the population has changed versus what was originally there. Now you're also going to see it like this, births minus deaths over your initial population value. Okay, so that's right, so that's a big one there. All right. So how much the population numbers are changing versus how much which was originally there. Okay, so if you look at numerical response 5, again on your unit test, that says, what is the projected per capita growth rate of the grizzly bear population in the North Cascades, British Columbia from 2001 to 2050. So they're expecting 150 bears. So remember that they have an initial population value of 23. We want 150 minus 23, and that's going to give us a value. Now there's no units for per capita growth rate. We compare it to 1. So it's expected that you should have about so every current individual will have about 5 offspring, right? So there'll be about 5.52 bears per each member of the population here. So think about population bottlenecks with poaching with that, right? If we regrow the population, that means every individual of that bottleneck is really, really important for reproduction. So we have to ensure their fertility. Okay? So that's per capita growth rate. In your text, in your key, on page 130, there's another good one here. It says, many elk live in and around an 80 square kilometer area that includes the Jasper town site. The elk population of this area at the beginning of a study year was 500. If there were 35 births and 5 deaths throughout the year, what was the per capita growth rate of the elk population? Okay, so you have an initial population of 500. So NI equals 500, right? And there were 35 births and 5 deaths. So your per capita growth rate question is CGR equals 35 minus 5 over 500. And that's 30 divided by 500. So your per capita growth rate value is going to be 0.06. Okay. And that is 9 is B on page 130. Okay. So there's one more way that you might see this as well. Okay, so let me give you an example. Let's say in Amazonian parrots. At a population of 98 individuals, had 15 births, but 6 survived to the end of the season. What is the per capita growth rate of the parrots? Okay, so here's the deal. There's 15 births, but only 6 survived. So that means 15 minus 6 would give you the amount of deaths, right? So this would be, so your CGR is births minus deaths over your initial population. So you know that there would be 9 deaths, right? So 15 minus 9 would be 6. So I would use this value. 6 over 98 would give me my per capita growth rate. So I don't use this value because the births are insignificant here because there was deaths, but the deaths aren't stated, they're inferred. Okay? So not a hard question, but it's something that it's an easy thing to get messed up that you need to be able to pick out. So my per capita growth rate again here would be 0.06. Okay. So, almost done equations that you guys need to know. Actually, I think that is the last equation. So you guys have Hardy-Weinberg, right? That was the whole first half of the unit. You need to know your density equations. You need to know your growth equations, your growth rates, your per capita growth rate equations. Okay, these are your equations that you need to know.